para presentar. Allá está. It's not. Okay. Good afternoon, everybody. It's my pleasure to introduce Professor Arthur McDonald, who will be delivering the colloquium today. Professor McDonald was born in Sydney, Nova Scotia, in Canada. He graduated in physics from Dalhousie University, also in Nova Scotia, and then he moved to Caltech for his PhD. Later, he also worked at Chalk River Nuclear Laboratories in Canada, and then moved to Princeton for a faculty position. Since 1988, he became a professor at Queen's University and director of the SNOW experiment. Art has a long list of honors and awards. I'm just going to talk about 3 of them. He received the 2007 Benjamin Franklin Medal in Physics, as you all are aware, the 2015 Nobel Prize in Physics, and also the same year, the Fundamental Prize in Physics. Art is also a member of the Order of Canada, and that's recognition for outstanding achievements for people in Canada. He always has been very supportive to students and early career researchers. He's here this week because our institute is hosting the Deep Collaboration Meeting this Saturday, Sunday, and Monday, where the collaborators from the UK, Canada, the US, and Germany are coming to discuss the latest results of what it actually is the largest operating dark matter detector in the world. So Art, thank you very much for coming to Mexico, and I hope that you are enjoying your stay.
Can you? Let's start by testing the volume level on this. Can you hear me at the back? It's okay? Good. Well, first of all, thank you, Eric, for hosting our meeting here. We're very pleased to be here. First time we have had a deep meeting hosted here in Mexico, although you have been a substantial part of our project right from the beginning. And Eric was the winner of a prestigious postdoc award at the SNOW Lab underground facility. We won a prize, the SNOW project did, called the Polanyi Prize, named after another Canadian Nobel Prize winner. And we looked internationally for a very good person to come and be a postdoc there, and Eric was chosen, was there for 3 years, did wonderful things for us in the beginnings of this experiment and has been back here at UNAM for about 3 years now, is continuing to participate in a very active way in the project. He has many students, I think 11 altogether if you include undergraduates and graduates. We have had a student from Mexico in the summer, a special program at Snow Lab for such things for several years, and that's an ongoing program. So our relationship to Mexico is a very positive one. I'm going to talk about the DEEP experiment, which is the liquid argon experiment that the collaboration meeting is for. I'll also talk a bit about the PICO experiment, which is another way of measuring dark matter, looking for bubbles produced when dark matter particles interact with our detectors. And the DAMIC experiment also has participants from Mexico involved. And so at Snow Lab, we're strongly represented in collaborations with Mexico. So let me say my wife Janet and I are very pleased to be here in Mexico City. It's a beautiful city and your campus is wonderful. And it's really good that the temperature has a plus degree in front of it instead of a minus degree. So let me tell you a bit about Snow Lab, about experiments in Snow Lab that will, we hope, enable us to observe dark matter particles, perhaps for the first time. But really, the subject of particle astrophysics, the ability to study our universe by going to a deep underground location, it's 2 kilometers down in a very active nickel mine, which enables us to use that rock to shield out the cosmic rays that otherwise would interfere with our experiments, but still look for particles that penetrate through that material, or to look for very rare radioactive decays in an ultra-clean environment. It enables us to do quite a remarkable set of things. We can really study the universe all the way from the most microscopic levels, from the particles that are some of the smallest that we know, such as neutrinos. We can study the sun. We can study neutrinos that come from uranium and thorium content in the Earth. We can study our Milky Way galaxy by attempting to understand the dark matter that influences the structure that we observe in our Milky Way galaxy. But we can also understand the particle physics associated with those dark matter particles and the neutrinos, and those properties influence the way in which the universe has evolved over the years, 13.6 billion of them since the universe was created in the Big Bang. And so with these laboratories at such a depth, we can study how stars like our sun burn, study in detail the nuclear reactions that power them, and really which are, in many cases, the nuclear reactions that produce the elements from which we are composed. It really is a little bit of our past history as humans. Study the basic laws of physics. We've been able to change the details of the standard model of elementary particles by determining new properties of neutrinos. What is the composition of our universe overall? Dark matter, we think, is about 26% of the total, and we have no idea what it is. We do that by measuring neutrinos that come from the sun. We did that with the Sudbury Neutrino Observatory experiment in the first place. We're searching for dark matter particles, which we think were left over from the original Big Bang, and we can measure rare forms of radioactivity, things that have half-lives in excess of 10 to the 26 years, which are processes that are extremely rare, but may help us to understand equally rare processes back in the early universe in which the equal amounts of matter and antimatter that we think were made in the Big Bang have now become unequal, such that you find yourself in a matter-dominated universe. And so trying to understand what happened to all the antimatter is part of the objective of those rare radioactivity experiments. So since this is a physics audience, but a somewhat more general, I'm told, physics audience, let me just take you back to a few first principles and remind you that along with electrons and quarks, neutrinos are very basic particles. We don't know how to subdivide them any further. They come in three flavors. They're described by the Standard Model. They only feel the weak force, and therefore they can travel through the distance that light travels in a year of lead, if they're at the energies such as they are emitted from nuclear reactions powering the sun. They can travel through a light year of lead with only a 50% chance of interacting with something. So for them, matter is essentially open space. They only stop if they hit the nucleus of the atom or the electron going around it head on. And so they're tremendously penetrating, which is great in terms of getting them out from the core of the sun to study the sun. Not so great when you consider the type of detectors you have to build in order to observe them. The original Standard Model said that neutrinos should not change from the type of flavor produced in the core of the sun, the electron neutrinos, to other flavors. If they do and exhibit oscillation properties, then that implies that their rest mass must be greater than zero. So if you express that in the standard formalism for the Standard Model, we have three types of quarks, three types of leptons in terms of the charged leptons, and three types of neutrinos. The processes that we're familiar with and the things that make us up are things that are in this column, in the sense that neutrons and protons are made from combinations of up and down quarks. The electrons go around the nucleus formed by those neutrons and protons, and that forms the atoms from which we are made. Neutrinos are unusual particles. As I say, they only experience the weak force, and therefore they're very hard to detect. They are produced in enormous numbers, as we'll discuss in a moment, by nuclear reactions that power the sun, and they also are emitted in certainly other radioactive processes like beta decay, and those are typically processes that involve a transition from one quark to another. So this, together with the force carriers and add the Higgs boson and the graviton, gives you a description of the standard matter that we are familiar with. And I'm going to switch batteries here on my laser pointer, unless you have another one to hand immediately, because this one's beginning to be a little bit fractious. But dark matter particles that we know from various astronomical measurements basically are influencing substantially our universe, those particles don't fit anywhere within that model. And therefore dark matter particles are something that it requires us to go beyond the Standard Model. Good. Would you mind replacing the batteries with these two? Thank you. There. So dark matter particles are something completely different. If we observe them, therefore, and that'll be a large part of my talk, then what we've done is we've done particle physics at an extremely fundamental level, but we've also contributed significantly to our knowledge of the composition of the universe. Let me start by talking about neutrinos from the sun, because that is the science for which we were awarded the Nobel Prize, along with the Super Kamiokande experiment studying atmospheric neutrinos. We studied neutrinos from the sun with the Sudbury Neutrino Observatory experiment. We studied electron neutrinos produced by nuclear fusion reactions that power the sun. We studied the boron-8 neutrinos, and starting with the pioneering experiments of Ray Davis in 1968, for which he received a Nobel Prize for his pioneering work, there was a puzzle in terms of the numbers of neutrinos that were observed. These are the thresholds in which various experiments, 1968, 1989 for Kamiokande, and later in the 1990s for its successor, Super Kamiokande, studying with a threshold up here and really only studying the boron-8 neutrinos. From 1992 on, several gallium experiments studying the lowest energy neutrinos. All of these measurements found too few neutrinos in comparison to what was calculated by very models that matched how the sun burned very well and matched the known properties of the sun in a very good way. So we were faced, prior to the results of SNOW, with what had come to be known as the solar neutrino problem, which was that the calculations, which was known as the standard solar model, here you have the calculations and the uncertainty on the various components for these various types of neutrinos from the different nuclear reactions powering the sun. The gallium experiments here showing a little over 0.5 compared to theory, the original chlorine experiments and subsequent versions of it about a factor of 3, and then Kamiokande and super Kamiokande both seeing only about a third. All of these experiments, either exclusively or predominantly, were studying only the type of neutrinos that are produced in the sun, electron neutrinos. And therefore it was not clear whether neutrinos were changing their type and eluding their detection, or whether the calculations of how many were being produced were incorrect or incomplete. Back in 1984, Herb Chen from UC Irvine, who actually passed away a couple of years later from leukemia, proposed that if we had 1,000 tons of heavy water, we could make two measurements. One which was specifically for the electron neutrinos produced in the sun, and the other which was equally sensitive to all neutrino types. And therefore we could resolve the question by comparing those two as to whether or not the neutrinos were changing their type, because we didn't need recourse to the calculations in order to make the measurement. We had both components at the same time. And therefore, if we were able to do that experiment, we could resolve the question. You see, with heavy water, and about 1 in 6,000 molecules of water is actually D2O rather than H2O, and Canada had reserves, and we were able to borrow 1,000 tons, $300 million worth for about $1, which is kind of one of the best investments I think that we could make. We had to pay about $1 million in insurance by the time we actually received it, but we were able to do this experiment, and in it we looked predominantly at two specific reactions. One in which the neutron in the deuteron is changed into a proton and a fast-moving electron, which makes Cherenkov light in the water. And a second one in which the neutrino, really any neutrino type with equal sensitivity, could break apart deuterium into a neutron and a proton, producing a free neutron in the heavy water, which has a very long mean free path in that material. And we had three different ways of detecting those neutrons, and so we were able to make measurements where we compared those two reactions. If this is the total, and if this is only 1/3 of the total, then we have an explanation for what is happening. 2/3 of them are changing into the other neutrino types from electron type neutrinos. And that's in fact what we observed. But in order to do it, we had to be very careful about radioactivity, because any gamma ray greater than 2.2 million electron volts was capable of doing the same thing as this neutrino is doing. And so we had to restrict the radioactivity tremendously. We ended up with water at the center of the detector, heavy water that had less than one radioactive decay per day per ton of water for the uranium and thorium chains. And that is something that had not been done before, and it's an indication of the fact that really all of these experiments require the development of new technology in order to be able to be accomplished. Same is true of our dark matter experiments. So now what I've done is shown you the same plot where you see the previous measurements with our measurements from SNOW. Here's our measurements for the reaction that is sensitive to electron neutrinos only. And in fact, it's 1/3 of the total. Here's the sum of all neutrino types, and it agrees within the error bars, and in fact, ultimately is even more accurate than the theory now, with what you would expect for the solar models, confirming that the solar models, in fact, are very, very accurate, and that we know how the sun burns with great accuracy. The difference, actually, between these accurate measurements of Super Kamiokande and snow is due to a small sensitivity in the elastic scattering of neutrinos from electrons, which is the principal measurement that was made in Super Kamiokande, and the charge current reaction, so-called in snow, that I showed you on that last transparency. And that difference is another way of measuring whether neutrinos are in fact changing their type. And our first paper at a 3 standard deviation level used that data from Super Kamiokande to show the first indication of something that was occurring. But it was our second paper in which we used our own data, which is shown here, that enabled us to show that with that sort of accuracy on electron neutrinos and this sort of accuracy on all neutrino types, that 2/3 of the neutrinos were clearly changing from electron neutrinos to other neutrino types, with about a chance in 10 million, or in other words, 5 standard deviations, indicating that neutrinos had changed their type in transit from the core of the sun to the Earth. That was a measurement then, but in order to do it, we had to do a rather extensive development process for the snow experiment. Well, first of all, we have had great cooperation from mining people in Sudbury. This was the original site of the snow experiment. It's in an active mine. They're taking 5,000 tons of ore a day out of that mine at the same time as we do our work, which for us is a great advantage because they maintain the mine in pristine condition. They have been very cooperative with us, and we travel in the same mine cage as they do. It's deep. It's 7 Eiffel Towers deep. I guess it's 20, what's the name of the? Latin American? 20 Latin American towers deep. I didn't quite get that information in time to get a picture to put on here to give you the right answer. Actually, when I'm in the United States, I usually use the entire state building. Now, you may think I got that wrong, but when I was a professor at Princeton in the 80s, and my son, who was about 8 at the time, took a school trip to New York City, and he came back and told us they'd seen the entire state building. So that's an icon you can use as well. It's deep. It's great in terms of reducing the cosmic rays, and it really was not a substantial problem in our experiment. And it's something that we have will use to our advantage in SNOLAB, which is at the same depth. So here you see the 1,000 tons of heavy water in a 12-meter diameter acrylic sphere, surrounded by 18-meter diameter photomultiplier support structure with 9,500 photomultipliers looking in at the central region. It's all bathed in water, in a water and radon-proof environment. And this was all constructed with people working in ultra-clean environment. Everyone took a shower, changed into clean room clothing like you would in manufacturing semiconductor chips in order to build the entire detector. The construction of that acrylic sphere took us several years, a lot of work to do it. Everything had to be cut into sizes appropriate to come down into the mine and rebonded. It was all done under ultra-clean conditions. By the time we were finished, we estimated that we had less than a gram of dust, mine dust, on the entire detector, about less than the amount you could pile in your thumbnail on the entire detector. And we had to do it in order to accomplish the experiment, but ultimately the radioactivity was about 10 times lower than the signal, and gave us a good signal to noise. This is the equipment that was used to get that low 1 radioactive decay per day per ton of water, a billion times better than tap water. We were visited twice by by Stephen Hawking, an absolutely amazing individual who at this point in 1998 could use his right hand to control his wheelchair and to ask very good questions of our graduate students in the underground location. The nickel company, Inco, designed a special rail car to bring him down so that he could be vacuumed off above ground and brought underground without any contamination. An absolutely inspiring individual, and particularly in the way that he has continued to do his science in spite of his disabilities. I think everyone who met him felt the same. So, neutrinos oscillate. What is the mechanism behind that? Well, if you're physics students, I'm sure you have learned this. The model that works for this is that you start with flavor states. You produce electron or muon or tau neutrinos in association with the other particle. But when they travel, if they are composed of, if these quantum mechanical states are composed of states of mass, much more prosaically named mass 1, 2, and 3, then as they travel, the mass fraction changes. And so when you ask at a later time, after they've transported over some distance, whether you have an electron neutrino or the other types, you will find that the wave function doesn't look exactly like it started out as exactly an electron neutrino. The probability can turn out to be, as it was in our case, 1/3 electron neutrino and 2/3 muon and tau neutrinos. And so if you look at it in a more mathematical formalism, of course, the Pontecorvo-Maki-Nakagawa-Sakata matrix, you say, all right, you can express the flavor eigenstates in terms of mass eigenstates with a 3x3 matrix. That matrix, it turns out, breaks down into components where the C's and S's in this equation are cosines and sines of angles that are used to describe the oscillation process. And it turns out that they're almost independent of each other, assuming that the masses of, for example, 1 and 2 and 2 and 3 are significantly different from each other. So that's the matrix that gets defined by measurements of atmospheric or typically accelerator neutrinos. That's the matrix that gets measured by solar or reactor neutrinos in terms of the parameters that are associated with doing those experiments. And so these two matrices and these masses are what define those sets of measurements. And basically, in each case, you end up with an oscillatory behavior in which the parameters are a difference in mass between 1 and 2 or 2 and 3, and an angle out in front, which is typically labeled theta 1, 2 or theta 2, 3. And these parameters have been defined. I'll show you the current status in a moment. There has also been a significant definition of the 1, 3 parameters. But in terms of an overall picture for how neutrinos, how we understand neutrino properties, there are still several things to be defined. And that's the subject of future experiments. For example, this particular parameter is one that violates CP, and this may be similar to what affects neutrinos when they participate in the mass asymmetry processes in the early universe. This is an addition to the matrix when you use the same parameters to understand double beta decay. These are the parameters that affect oscillations, and this is added on for double beta decay. These are also CP violating phases. And so measurements are going on. The Dune experiment, for example, at Fermilab is aimed at this parameter and also at mass hierarchy. The double beta decay experiment, I'll mention one that's going on at SNOLAB. This is my colleague Takaaki Kajita, with whom I received the Nobel Prize. for the work that was done at the Super Kamiokande experiment, in which they used a detector about 10 times the size of snow filled with light water to study the oscillation of neutrinos. And this is a version of the data that they obtained, in which they are looking at the probability as a function of the parameter L over E, which is the one that defines the oscillation process. And you can see that oscillation is the favored choice over other possible explanations for this data. So this is one example in which oscillation is observed. Camland, in an experiment that was first reported in 2002 and thereafter, looked at reactor neutrinos in Japan and again observed an oscillatory pattern. And this is a further oscillatory pattern observed for T2K. So there's an interesting and fairly simple conclusion you can draw from the fact that you actually see neutrinos oscillate in these particular ways. Murayama is the one I've seen put this forward. And he says that if neutrinos are going to behave in an oscillatory way, they have to have the ability to sense time in their rush frame, in the frame that's traveling with them. If they cannot sense time, then they cannot behave this way. If they are traveling at the speed of light, then they don't have that ability to mark time in that rush frame that's traveling at the speed of light, and therefore they cannot be traveling that fast. Therefore they must be traveling less than the speed of light and must have a finite mass. And so it's, to me, a relatively straightforward way of seeing why is it that if you observe oscillations, you must have a finite mass for neutrinos. Another way to look at it, of course, is that the model that works very well is one that involves differences in mass between neutrinos expressed in terms of mass eigenstates. And here is a plot, a very complex plot, of essentially all the measurements that have been done on neutrino oscillations since day one. What you see is a plot of differences in mass versus the tan of the angle involved. And everything is put on the same plot, whether it's 1, 2, 2, 3, 1, 3, and so on. But remarkable progress has been made, given the fact that it's only in 1998 and 2002 that for the first time we knew that neutrinos did oscillate and have a finite mass. We now know, based on the work at Super Kamiokande and some other accelerator experiments, fairly well the parameters for 2, 3. Based on solar neutrinos in Camland, we have parameters for 1, 2. Based on the 1, 3 experiments, Diabe, Reno, for example, we have fairly well-defined 1, 3 parameters. And we're closing in on the delta parameter, although that, I think, will wait for Dune in order to get a firm definition. We know from the fact that show you in a moment something else just for fun. We know from the fact that there is matter interaction that perturbs the standard formalism for neutrinos interacting in the sun. They actually interact with electrons as they pass through the sun. They come out in a pure mass 2 state and stay in that state before they reach the Earth. That can be used to define the relative size of mass 1 and mass 2. In other words, the hierarchy between mass 1 and mass 2. What we don't know yet is the hierarchy for mass 3. And so that is still to be defined. We don't know whether neutrinos are their own antiparticle, which they have to be in order to participate in neutrinoless double beta decay. We don't know whether they are Majorana neutrinos. We know differences in mass. We don't know the absolute mass. We don't know that parameter delta Cp that I mentioned earlier. We don't know whether this theta 2,3 parameter is maximal or not, and in terms of trying to come up with proper theories for neutrinos, that question is a big one because it overlaps 45 degrees, and probably the accuracy in the future experiments will define that. We also have a number of conflicting experiments that deal with the possibility of a fourth neutrino type, which would have to be sterile. Now, okay, so I've had a heck of a time trying to define to the general public why neutrinos oscillate. The first week after the Nobel Prize, I was interviewed multiple times in television, et cetera, and there's a comedy program in Canada that tries to pick up on the news, and particularly go and bother politicians and try to catch them out on things. But anyway, they sent me a script about neutrino oscillations, and just for fun, I thought I'd play it for you, because at this point in the talk, 50% of the audience is usually asleep, and this is intended to try to wake you up. It's not normal in a physics colloquium to do something like this, but Eric thought it might be fun. So you have to understand that in Canada, Tim Hortons, if you visited Canada, you know that the coffee chain Tim Hortons is in every street corner. In fact, the definition of whether you live in a small town is whether you can stand in your Tim Hortons and look out the window and see another Tim Hortons. If you can't, then you're genuinely in a small town. And it also may not surprise you to know that Tim Horton was a hockey player. So anyway, let me play this for you, and you might appreciate it, because I'm sure many of you have tried to explain neutrino oscillations to the general public and may have experienced something like what I experienced. So let's see if this works with the volume and so on. Well, it isn't. So we're not getting any sound.
McDonald is Canada's latest winner of a Nobel Prize. Here to explain why he's the best in the world.
Turn it up a little bit more if you can.
McDonald.
Hi, I'm Art McDonald. I'm
maybe it's
Professor
okay.
Emeritus at Queen's University, originally from Cape Breton, and I attended Dalhousie University. And I'm a co-winner of the 2015 Nobel Prize in Physics. People from 22 Minutes have asked me to come in and explain what I and our team did to win this prize. We demonstrated that the flavor of neutrinos produced in the core of the sun, electron neutrinos, changed into one of the other two flavors, muon and tau neutrinos, as they travel from the core of the sun to, okay, I'm being told I have to make it simpler. Neutrinos are very basic subatomic particles that we don't know how to subdivide any further. And okay, they're asking me to dumb it down a little bit. A subatomic particle is smaller than an atom. Atom is a unit of matter. Really? You don't know what matter is? Grade 7. Okay, neutrinos are like Timbits. Sometimes they're like chocolate, sometimes they're like cherry filled, and sometimes they're like the old-fashioned glaze. I must be the first person that ever won a Nobel Prize in Timbit.
If Eric tells me that if it were to be translated into the Mexican context, tamales rather than Timbits, which are little donuts with red, green, and sweet, I think is the three types. All right, so you can have, as I was telling the students, you can have fun with science. It really, all of this has been a real fun experience. And it's quite remarkable what now we believe we understand. We always constrain ourselves by saying that we understand what we can measure. We think that we understand a fair amount about what has happened in the last 13.6 billion years since the Big Bang, since inflation. Subsequent to that, in a very short period of time, when the temperatures were enormous and the energies were very high, you end up with a soup of the most fundamental particles, electrons, quarks, and neutrinos being the the basic ones, but maybe also dark matter particles. We don't know about them yet. As it cools off by expansion, the quarks combine into neutrons and protons. Even 3 minutes later, which is when you start to see them begin to coalesce, you still have a pretty foggy universe. You're not seeing very much until you get to about 300,000 years when you have atoms forming, and then you get structure formation, which is influenced significantly by neutrinos and by dark matter particles. Their interactions and the question of how massive they are has an effect. Now, there are a number of questions. I mentioned earlier, where did all the antimatter go? And we attempt to address that by neutrinoless double beta decay. What is the absolute mass of neutrinos in terms of their influence? Same sort of approach, neutrinoless double beta decay. And a very major question, what are all of these dark matter particles? Let's start with an experiment that is now about to, it's running in the former snow detector with pure water everywhere, but ultimately we'll have liquid scintillator in the central region with about 4 tons of tellurium, of which about 34% is the isotope tellurium-130, which is a prime candidate for neutrinoless double beta decay. And so we hope to have one of the most sensitive neutrinoless double beta decay experiments in the world. We had to make a big conversion of the snow detector. We had to hold down the central volume because this liquid scintillator is now lighter than the surrounding water rather than heavier. And it has gone very well. We expect to be in operation with scintillator next year and with tellurium the following year. So here's this very complex topic all on one slide, just so that you get a feel for what's involved. If in fact you have a situation where the neutrino is its own antiparticle, then you can have a process, unlike the normal 2 beta decays, which emit 2 neutrinos and 2 electrons. You can have a process where essentially the neutrino is reabsorbed as an antineutrino and no neutrinos are emitted, which is then monoenergetic in the sum energy of the 2 electrons. And that's the peak you look for in these experiments. Turns out that the half-life for that is represented here with a form factor, a matrix element for the nuclear physics, and an effective mass, which is actually using all of those various now measured thetas, 1, 2, 1, 3, and 1, 2, and 1, 3 in this case, and then the 2 additional phases I mentioned. If you then plot what you expect for that effective mass versus the lightest neutrino of the 3, then you get a plot of this nature where, depending upon the hierarchy, whether it's inverted or so-called normal, you follow this line, where the limit right now for the mass of neutrinos is at about, for this parameter defined in neutrinoless double beta decay is about 0.2 electron volts. It is hoped that in future experiments, so we'll be able to get down to 0.1 or even lower, and that implies half-lives on the order of 10 to the 26th years or greater in order to make the observation. In snow, with liquid scintillator and with 1,300 kilograms of the isotope tellurium-130 and 3 times that of total tellurium, we hope to get a half-life that would enable us to get down with uncertainties associated with nuclear matrix elements into this range below 0.1 electron volts. And there is the possibility in the future of something even stronger in terms of its capability, because in fact these tellurium compounds we've been dealing with are quite transparent. So that's our status of neutrinoless double beta decay. The remainder of my talk will be about dark matter, which is the subject of the experiments that we're having the collaboration meeting here. And of course, I'm sure you've seen these plots of what our thoughts as to how the universe is composed now. Us, only about 4%. That standard model I showed you earlier is only a fraction of the total mass energy component in the universe. Dark energy, resulting from observations of far distant supernova, may be Einstein's cosmological constant, or it may be a form of energy that would contribute 70% to the total. Dark matter appears to be about 26%, be very weakly interacting, and may take the form of weakly interacting massive particles, which is what we're looking for, or possibly axions, which are a completely different animal and something detected in a very different way. With our laboratories underground and very little interfering radioactivity, it's possible for us to look for dark matter particles produced in that enormous energy back in the Big Bang, banging into our detectors and producing a phenomenon that we look for. At CERN, they're attempting to create dark matter for the first time since the Big Bang by having enough energy to create the mass required to create dark matter. It turns out that if you plot the speed of stars in galaxies, spiral galaxies like our Milky Way, others similar to it, what you find is that the measured speeds are far different from what you would expect if you simply said that the matter is being held in place by the gravitational force of the glowing matter. There are many other ways in which we determine that it must be weakly interacting. Gravitational lensing, development of large-scale structure in the universe, and so on, requires us to have slowly moving and massive dark matter. It's not been observed so far in experiments at CERN. It is weakly interacting. That appears to be the case, and massive. And so WIMP is a wonderful whimsical term to use for these particles. We look for them in terms of their interaction with ordinary matter. A lot of theoretical predictions of particles that might represent this. Our attitude is we will attempt to make measurements that go as far as they possibly can in terms of the possibility of detecting them, moderated a bit by the possible theory as well. So this is SNOLAB. Starting in about 2003, the laboratory was expanded from the original area, 2 kilometers underground, representing snow, to other spaces on the same level that expand the excavated volume by about a factor of 3. The specific allocation of money by Canada was to bring other countries to Canada to work with Canadians in national laboratories. There were 3 different types of laboratories produced by the $100 million that was put on the table to try to make that happen. We have been able to do that. We are bringing a lot of people from around the world, including people from Mexico, and we hope even more so in the future, to work with us here in Canada. And it's really the objective of the laboratory. Of the set of experiments that are in the laboratory, the ones in red are the ones in which Mexico is participating. There are experiments in dark matter. I'll talk about DEEP, for which we're having our collaboration meeting. I'll talk about PICO, in which Eric and his students and postdocs have been very instrumental. I noted earlier DAMIC, which is a very ingenious approach to dark matter detection using highly pixelized detectors to discriminate against background. And next year, Super CDMS, which is one of the highest priority projects in the US, will be also cited in SNOLAB. It's clean. It looked like this back in the snow days, and my mother visited. And she said, "It looks pretty clean, dear." I think she was amazed that I could, at the time I was responsible for something that was that. She'd never seen anything like that before. But Anyway, the whole laboratory is clean like that, and that's great when you're trying to control dust in experiments. You can put a little tent or a container over your experiment and get a factor of 10 better than the factor of 2,000 that, in fact, we have everywhere. Stephen Hawking came back. Here you see him surrounded by many people in the cryopit, which is an unassigned area so far. The DEEP experiment. Collaborators from Canada, UK, and Mexico, including this institution. We've had excellent collaboration with Eric over a number of years, and I mentioned earlier that he was a former Polanyi postdoc at Snow Lab. It's a complicated experiment. In this case, it looks somewhat like the SNOW experiment in the sense that there are, in this case, 275 light sensors looking in at a central volume housed in an acrylic vessel. In this case, the dimension, however, is about 2 meters across rather than 12. And this is filled with liquid argon, which is about 200 degrees below zero. It's 87 degrees Kelvin. Light guides to guide the light to the photomultipliers. The idea in this experiment is to just use light in order to discriminate against background. And I'll show you in a moment why argon is ideal for that. 3,600 kilograms. We're actually running with the detector at about this level, 3,300 kilograms. Some difficulties with possible leak here in the neck leading us to do that, but it's been running very well that way for about a year. Wavelength shifter on the inner surfaces here that convert from the 125 nanometer light produced by events in liquid argon to visible light for the photomultipliers. The transparency is great for the light going across the vessel. Extreme cleanliness again, including a final resurfacing of the inner surface to remove radioactivity that has been deposited there by radon deposition during the construction. Argon has a property that for the higher density nuclear recoil, higher energy density nuclear recoils, you have a lifetime for light emission that is dominated by 6 nanosecond lifetime for de-excitation of the argon atom. For minimal ionizing particles, for electrons and gammas, that lifetime is more like 1.5 microseconds. Very big difference between the two, so that an electron-like event looks like this, a small amount at the beginning, and then continued light over, in this case, up to 5 microseconds. Most of the light in a nuclear recoil, we can simulate this with using a neutron source, looks like this, and it is these nuclear recoils that we are looking for from WIMPs interacting with the argon in the detector. And so we use a parameter which is the amount of light in this prompt region compared to the total, and that's what's plotted on the left axis here. And all of the gammas and betas basically show up in this region here, including gammas from an isotope of argon that is produced in atmospheric argon by the cosmic rays in the atmosphere. And therefore, we have a need to get special argon that comes from underground sources. And I'll tell you a bit about that as well. So we see alpha particles from surfaces showing up in this region where you produce a recoil band. But we also are able to understand them in great detail, and we are working at having zero background down in the very low energy region down here where the WIMPs induce recoils. It's a very nice picture actually from National Geographic magazine of what the detector looks like. This shows you what the device for resurfacing the inner surface is. We've been able to meet our targets very well for the radioactivity in the detector, and particularly very low radon content in our argon in the middle, more than a factor of 10 better than other experiments attempting to do the same thing. We can understand the detector in terms of the radioactivity residual in various components, such as the photomultipliers and the acrylic and so on. And this black curve here is the data, and it's almost matched by the sum of all of the different components that come from radioactivity in the various materials. And so we think we understand quite well, for example, how many neutrons are produced by alpha N reactions in the vicinity of the detector. Pulse shape discrimination, based on those 2 lifetimes I mentioned, is extremely good. This is what it looks like in the region of interest. You can see this parameter is actually the amount leaking through a threshold in this prompt discriminator value as a function of that value. And you can see that, for example, for 50% efficiency for nuclear recoil acceptance, you're getting down to on the order of 10 to the 10th in terms of the ability to discriminate against electrons and gammas. We've been running for about a year and a half now. We presented a paper last summer on the first 4 days of data, just to indicate to the world that the detector is running very well. This is the region where you would expect WIMPs to show up. This is F prompt again against photoelectrons, which is a measure of the recoil energy of argon nuclei. This is background from the argon-39, well out of the way. We saw nothing, and by doing that, we were able to set a limit, which was, as shown here in the dark blue line, the equivalent of what had been done in the dark side, the previous argon experiment. We'll be discussing in these collaboration meetings residual background that we see from various sources, which we are very hopeful we can characterize in such a way as getting rid of it. We're down to the very few event level. In doing so, if we are able to get it down to 0, this is our ultimate sensitivity for 3 years of running, compared to other experiments working with xenon, including an experiment called Xenon 1 ton, which is the main competitor right now. With argon, we've got a major development in the last 6 to 8 months that brings some people here to our deep meeting, because people from other experiments are now participating in deep analysis, and we're also making plans for the longer term. This is a situation where all of the people working on argon internationally, a total of about 350 researchers, have come together with a long-term plan to move from deep at 3 tons to the dark side experiment with 20 tons and ultimately 300 tons, which would enable us to go all the way down to what is referred to as the neutrino floor. You can see the large number of institutions, including your institution here in Mexico. Again, we're very pleased to have that involvement. The next step is 20 tons. It would look like this. It would be situated at the Gran Sasso laboratory, although even now, with help from CERN, we're making modifications to this design to try to improve on radioactivity and other elements of it. The approach that's being taken is a so-called 2-phase approach that was already taken in the dark side 50 experiment, in which, in addition to observing the light with photomultiplier tubes, you are able to observe the electroluminescence that occurs if you accelerate the ionized particles produced in the argon to a gaseous region here and allow them to emit light. And this also gives you a very good way of determining in an XY direction where the event was, and in a Z or Z direction through the drift time. In the dark side 20 experiment, we actually will replace these photomultipliers with a new type of photomultipliers made of silicon photomultiplier, and we have, in terms of large-scale silicon photomultipliers, the most advanced in the world from a company in Italy. The dark side 50 experiment has been extremely valuable in terms of understanding a number of parameters associated with this approach to things. This shows their results. This is using argon from an underground site, which is at least 1,400 times lower than what you would see if you had atmospheric argon. This shows you the argon-39 signal in the detector, and there's a bit of krypton in there actually, which dominates in the low energy region. And we intend to use underground argon in dark side 20 and also in the 300-ton detector. Cristiano Galbiati, who's here with us, and others have identified in a very nice underground site in Colorado large amounts of argon, which is at least 1,400 times lower in radioactivity than atmospheric argon. And we are just putting out a tender for the extraction from that site at 250 kilograms a day of argon that would be usable in the dark side 20 experiment. And in addition, it'll be further purified in a site in Sardinia, for which there would be a very large distillation column, and there's that Eiffel Tower again, 300 meters high for this distillation column, hoping to get factors of 10 to 100 further reduction in argon-39. Half of that column is currently being installed after being tested at CERN. So, with the ability to go down in, go up in the amount of background free argon and to count for long periods of time, we expect to be able to get down with argon to the so-called neutrino floor created by the coherent scattering of neutrinos with nuclei, which gives you a nuclear recoil which is indistinguishable from a dark matter particle. With argon, we have much better properties than xenon in terms of being able to discriminate events in which electrons are the result, such as the events that come from solar neutrinos, where for an argon experiment in the same range, you would have something like 30,000 solar neutrino events for one coherent scattering event. And they have demonstrated so far only a factor of 200 ability to discriminate against such events. We have, as you see, up to 10 to the 9th or so. And so we think that this leads us to a long-term prospect of working down to the neutrino floor, working also in the area above the region covered by the LHC, but also working in a very complementary area to what's being done at the LHC. And so our program will be moving from dark side 50 to deep to dark side 20K at 20 tons and on to 300 tons to really explore above about 10 or so or 20 GeV high mass WIMPs representing dark matter. PICO is another experiment at SNOLAB in which Eric has been a significant contributor along with his students. It's an interesting experiment in which what's done is to use the formation of bubbles due to the catalysis of a bubble by a nuclear recoil in a liquid, typically a liquid involving fluorine, which gives them a sensitivity to another way of interacting referred to as a spin-dependent interaction rather than spin-independent, as I've been discussing. It turns out that you can, with the proper selection of materials in detectors like this, get very good gamma and beta rejection. This shows you the probability of producing, of nucleation, it says, probability of producing a bubble at various thresholds for deposition of energy in the material. And above this threshold, for example, with this material C3F8, there's you can see 10 to the minus 11, essentially no production from gammas and betas, only production from nuclear recoils or from alpha particles, which can produce nuclear recoils. And they've also developed a very ingenious way of discriminating alphas from nuclear recoils that would be produced by WIMPs. The alphas are just basically louder because when you measure the sound at the same time as you're observing the bubble formation with a camera, what you find is that the long range of the helium results in much louder signals and very good discrimination against alphas. So it's an excellent discrimination against background, which is what you need. And so PICO has gone from success to success. They started with a 2-liter detector at Snow Lab, which has produced some very nice results. PICO 60 liters reported last February and is the leading experiment with a spin-dependent interaction. They're moving to a much cleaner 40-liter detector of a slightly different configuration, and ultimately they would like to go up at least a factor of 10 in a much larger experiment at Snow Lab. If you plot instead the spin-dependent cross-section, you see that the results of PICO 60 are the leaders for direct detection, and that they can move well down with their PICO 40 and 500 detectors. They even make a significant impact in the low, in the larger region where there were some finite results from DAMA in the early range. They exclude those results with their results from the PICO 60. So, deep in PICO, in which there are significant contributions being made by people here, both technologically and intellectually, are positioned to push the boundaries for high mass WIMPs with both spin-independent and spin-dependent sensitivity as we go forward over the next 10 years. They got excellent prospects for the future with argon all the way down to the neutrino floor. And those of us who are working with people from UNAM and others here in Mexico really look forward to fruitful collaboration as we go forward. And this science is very fundamental, very important, and it is science that has excellent prospects for the future, which was the answer to another one of the questions that the students asked me this morning. Thank you very much.
Thank you very much, Art.
Sure.
Such a nice presentation. We have time for questions.
There's actually another microphone here that, or you have them there. Okay, good.
Do you see any prospects for direct detection of the cosmic neutrino background?
Oh boy, that's extremely difficult. There is an experiment that's being pursued at Princeton called Ptolemy, which is, it's basically, well, it's somewhat similar to the approaches being taken by the Catron experiment. I mean, basically what one looks for is a small bump at the end of the tritium beta spectrum that might be representative of cosmic neutrino background. But the difficulties, I think, are substantial and maybe even fundamental in the sense that if you take that approach, and even if you take the other approach that's being taken for neutrino mass measurement, so-called Project 8, where they look at the radio frequency emission rather than looking at things in a retarding spectrometer like Catron, you end up with your sensitivity, or really your resolution, limited by the atomic physics of the tritium target that you're using. And so it may be extremely difficult. It's many orders of magnitude from what can be done with Catron or Project 8. I'm not really familiar with Ptolemy in detail, but I haven't heard any magic approach that gets rid of that problem of the atomic physics limiting you.
Yes, I would like to thank for the talk and especially for the opportunity to accept us in the collaboration. We will really look forward to extend the collaboration. We are very happy to be part of this collaboration.
So do we.
In all of this, dark matter has also has of course a gravitational effect. So you are assuming that there is another dimension beside the gravitational that you can measure in these experiments. Otherwise, it would be impossible to have a positive results. Is that correct? Or?
That's correct. I mean, what we're saying is that the gravitational effect is predominantly what has been observed so far. It's observed in the effects on the galaxy. It's observed in gravitational lensing. And in some sense, it's observed in terms of the effects of dark matter on large-scale structure formation and so on. But the assumption is that if this is a fundamental particle, and could be a WIMP or could be an axion, there will be some strength of interaction associated with that fundamental particle. We don't know how big it could be. So what we're doing is experimentally pushing as far as we can in the boundaries of what is possible to observe, and hopefully we'll be able to see it. But since we don't know what it is, it's hard to predict just what that should be. Yes?
Good afternoon. My name is Kenjiro. Where is the most astounding fact in the universe for you?
I'm sorry, would you repeat that? I'm going to turn off my mic.
What is the most astounding fact in the universe?
What is the most stunning fact in the universe? You see, the students ask all the simple questions. I thought I dealt with those this morning, but I think in the last 20 years we should be very impressed with the fact that we have been, maybe 30 years, we have been able to understand the last 13.6 billion years with a lot of facts coming together in a very concrete way to produce a quite believable story. You know, the fits that are done to a combination of cosmic background microwave radiation to large-scale structure to measurements of polarization of the CMB to just an enormous set of data that are fit with 6 parameters for what's called the lambda CDM, lambda being the cosmological constant plus cold dark matter being the dominant effects, leaving us still with what was referred to a few years ago as some known unknowns. The known unknowns being dark energy and dark matter. But nevertheless, we know in a sense what their characteristics are. And the rest of it is a picture that really fits quite well in terms of an understanding of where we came from, at least since the Big Bang. And to me, that's stunning. I mean, when I think back to the 1960s when I first got into physics, the idea that we would really understand how our universe has evolved with that degree of completeness at this stage, but still have fascinating problems to pursue, like dark matter and dark energy, I find it stunning, in your words. So,
Thanks.
thank you.
Accept.
Yeah, could you please comment on the Dama claim on the detection of dark matter?
Dama? Yes, I could. So I think the Dama experiment is very interesting in the sense that, well, at the very beginning, they were not terribly forthcoming in attempting to answer criticisms that people put forward. But, and they still don't make their data readily available, but they have done a pretty extensive job of attempting to answer many people who've come up with maybe it's this, maybe it's that, to explain their data. Radon in the mine, which turned out not to have the right, it doesn't peak at the right time to be what they're looking at, and so on. So I don't think anybody today can say there's a smoking gun experimentally that would say that data is incorrect. But on the other hand, it's very difficult for it to be reconciled with a whole series of other experiments that have not looked at the same thing, but have looked for effects that should be there if DAMA is seeing what it's seeing, and it really is dark matter of the type we normally think of, either WIMPs predominantly. And so it's still a big puzzle. I mean, you can't throw it away. It's absolutely beautiful sequence of data with many standard deviation accuracy, which oscillates over probably 10 years now. But it's also very difficult to say that it's dark matter. People just don't have the feeling that that's clear. And so there are several experiments now that are going to try to reproduce it, SABRE being one of them, which is being prepared to be run at Gran Sasso, but also be taken to the southern hemisphere, or at least some of the instrumental effects will be out of phase in terms of seasonal things. So I think it'll be very interesting to see what these other experiments see, because it's a rather specific thing that's seen, and I don't think anybody's found an experimental reason for why they're seeing what they're seeing. My opinion, anyway.
Okay, any other question?
You talk about the relations between Kaluza-Klein and Weyl theory. That relation?
I didn't talk about it. It's on one of my slides. I think, Fredo, you want to answer this question for me? You may be asking a question beyond my knowledge, but please say it.
Yeah, well, I was thinking that, is there any specific relation between those ideas from Kaluza-Klein in the 60s and the actual interpretation of the dark matter and neutralinos, something like that? Or the neutralino? Or dark energy?
I mean, Kaluza-Klein has also led to large extra dimension type approaches to some of these questions. I really think the relationship between that and, I mean, most of the other theory tends to be based on, in that region tend to be based on supersymmetric theories. And the relationship between those two, I think, is not strong. Fredo, you may want to make a comment since you're more of an expert at this than I am.
No, well, I would just say that in going beyond the standard model where you have several scenarios like supersymmetry or extra dimensions, you always look for ways to try to explain dark matter, and you have candidates. So, but there is no close relationship between, say, the neutralinos and Kaluza-Klein.
Okay.
Yeah. Sorry for my lack of detail
We have
understanding in that area.
one more question.
There are two types of neutrino, nuclear neutrino and thermal neutrino. What about the microwave background, the deep lower neutrino background? It is said that there is like microwave background, lower neutrino background.
Okay, so I think that's essentially what I tried to answer here, what's called the cosmic neutrino background. In other words, the cooling off of the universe since the Big Bang left us with microwave radiation that has cooled off to about 2 degrees or so. There also will be so-called relic neutrinos that were produced in the Big Bang and will have cooled off to a much lower energy or temperature, if you like, today. And those are the ones that I don't think anybody has yet come up with a really credible way in which you'll be able to detect those. I hope I answered the question you were asking.
Okay, any other question? General.
In your motivation, you mentioned the mother-antimatter asymmetry, and at some point you mentioned also CP violation phase from the neutrino part. Is there any expectation to get more information on CP violation in the neutrino sector?
Is there any, say it again, repeat
Any
the last.
expectation to get information on CP violation in the neutrino sector?
Yes, but of course, for the light neutrinos, as opposed to, for example, a heavy neutrino that might show up in the seesaw mechanism and then go on to be involved in an asymmetry process for matter in the early universe. The approach that's being taken for accelerator experiments is to look for differences in the oscillation pattern for neutrinos and antineutrinos. And by comparing those two, to look for that parameter delta, which in the formalism, which extrapolates flavor in terms of mass eigenstates, is a parameter that is CP violating. And that delta CP, as it's called, is the objective of the so-called Dune experiment at Fermilab, would be also the objective of Hyper-K experiment in Japan. And so the hope is to observe that particular parameter. There are also CP violating phases in neutrinos double beta decay that could also be an indication of, for the light neutrino system, the degree to which CP violation occurs. But the one that's the target of the majority of the effort these days is delta CP in the Dune experiment. Okay.
More questions? Okay. This is a really cool science, right? Okay, let's thank Art again. Thank you for coming.